checking, make sure I do this correctly. 1, 2, 6, 0, 3, 6, 0, 2, 4, 2, 4, 6, 7, 9, 3, 6, 9, and 6, 7, 8. Okay, so this is the first thing I went through. I scanned and I kept a count for each of these. Right? So if this was really too big, I probably could have used this Mischigrees algorithm to keep these approximate counts instead. But I kept a count for each of these. And so now let's say I want to find all co-occurrences, or 3 things together, that occur in at least 1/3 of all of the tuples. Okay, so now find, subsets in 1/3 of tuples. Okay? So if that's the case, I have 12 tuples, so they need to occur in at least 4 of the tuples. Okay, so that means that these subsets cannot include 0, cannot include 1, and so it cannot include 4, 5, or 8. Okay, so I did okay. I got rid of about half of. I got rid of half of the items. So now I need to look at all pairs which are made up of the five remaining things. And so now, my set S1 is going to be 2, 3, 6, 7, 9. And so then S1 cross S1, and I'm going to ignore things that occur twice. This set is now going to be 2, 3. Let's 2, 6, 2, 7, 2, 9, 3, 6, 3, 7, 3, 9, 6, 7, 6, 9, and 7, 9. Okay, so how many do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So if this fit in memory, then this will also fit in memory. Right? I only have 10 pairs I have to consider again. So now I can go and scan through this data set one more time and keep counts for these pairs. And I know it can't be any of these other pairs, right? So now I go back through and I see this is a little bit trickier to keep track of, but I have a 2, 3. I have a 3, and that's it, right? And the first set. That's the only interesting pair. And the second tuple, I have a 2, 6. I have a 2, 7, a 2, 9. I have a 6, 7, a 6, 9, and a 7, 9. That was a smaller tuple, but it happened to be a much more interesting one. So 1 is not anything. So 3 is an interest. So 3, 6 for the third tuple. Now I have a 2, 6, a 6, a 2, 9, and a 6, 9. 7, 8 says nothing. I have a 2, 6. I have, tuple 7. Now I have 3, 6. Is the only interesting thing. And T8, that's nothing. T9, nothing. T10, I have, let's see, I've got 6, 7, 6, 9, and 7, 9. T11, I have 3, 6, 3, 9, and 6, 9. And then T12, I have 6, 7. Okay, that's it. And so now I look, if I want it in 1/3 of all the tuples, this needs to occur at least 4 times. And the only one interesting here is this one here. This items 6 and 9 are the only ones that occur together at least 4 times. So on a small data set, this is probably not that statistically interesting, but on a larger data set, you know, when these have very high co-occurrences, this may be some interesting relationship.
So we can do something in the first pass so that for the second pass we don't have to scan over all the data. And similarly, if we are going for the further more passes, we don't have to scan over all the data.
So how would I avoid scanning over all the data without recordings? So if I just had this,
no, yeah.
So I would have to keep track of something else, right?
Yeah.
Okay, so what else would I keep track
of? The tuple in which they occur.
The what?
The tuple in which they occur.
So instead of a count, I have pointers to the tuples.
Yeah.
Right, so now instead of just keeping a counter, which is just log n space, right? Now I need to keep for every one of these things. It could be that, you know, if 2 occurs in 1% of all of the tuples, maybe this one occurs in 10% of all the tuples. That means for this I need to keep m divided by 10 pointers in just this one, which is a lot. I'm actually then this data structure is storing as much as my entire list of tuples, right? If every tuple has something interesting in it, then this data structure, which has a bunch of pointers, may actually get pretty big and pretty unmanageable. It may not fit in memory. So it's a little. This seems like it's too simple, but it's really better to make kind of 2 passes here. You usually don't need to make more than 2 or 3 passes. You can, what happens on the next round here is because there's only one thing surviving, I know I can't have any triples which occur in 1/3 of all the tuples. But, so I can cut down afterwards, because afterwards I can say all possible things that occur after this. But if I keep too much information here, it may not fit in memory.
You'll not have to keep more than m pointers. Only m pointers. Because once it occurs, once T1 occurs, you don't have to add that again.
Yeah, so typically people say that n, the number of products, may fit in memory, or it may not even do that, but m probably does not fit in memory. So even if you had m pointers, that's probably too much. And then keeping a data structure for that. So there may be ways to do it where you can actually, as you start filling up long lists, you kind of write them out to disk. But then you have to read through them again. If you have m pointers, you have to read through again. You might as well just read through the original data set. Then you don't have this extra storage of size n. So this you can do much more compactly. And you can actually use exactly the frequent items algorithm, the Mischigrees algorithm we talked about earlier, to do this. And this will give you an approximate answer. And that's very small space. So that should be even faster. Yeah, so after this, I know the only interesting pair is the 6 and the 9. And if you just looked at this, you may not have realized that those co-occur a lot together. So it's not data that easily kind of pops out by just looking at these sets. But by running through this very kind of simple algorithm, you can kind of pick out these co-occurring things in a very efficient, even on very large data sets. So there are a number of variations on this where people try and speed this up. They try and kind of look at samples of this first, or they try and maybe run niche agrees on this first step, or maybe keep some extra information so they don't have to do it. There's lots of follow-up work, or maybe they say, I want this to be, I want to also look back and say 6 and 9 occurred a lot together, but 6 actually occurred in 7 of the tuples, 9 only occurred in 4 of the tuples. So if I know they're going to buy 6, that does not mean they're going to buy 9, but if I know they're buying 9, they're probably going to buy 6. So this may be more interesting. You can start to try and make some claims like this. Okay, so this was basically all I wanted to say about this a priori algorithm. There are other variations of this, and it's used for a lot of these things, but if you're really doing this on Amazon, you really want to build a good model, you may actually do something other than this. And there's a lot of work on this, and this is something you should probably know if you take a class in data mining. This is kind of cool how it can filter things like this. And this idea will actually show up if you're trying to count triangles in graphs. By counting triangles, you want 3 vertices, which are all of the, so 3 people in a graph who are all friends with each other. You kind of use a similar algorithm where you kind of filter out things on the way. And if you want to find cliques in graph or something like that, you kind of do these similar several pass filtering algorithms. And these work fairly well, different variations of this. So you should be aware of these ideas. So one trick to speed this up is to use the Mischigrees algorithm or something in this step. Another thing you want to do is to kind of, after you get here, if you want to try and figure out what are the possible triples, and you have a larger data set, it may not be so obvious which are the available triples that you can do. You need to check whether you would then run through this set S2 and see which of them had over 4 items, and you would kind of put this, you want to kind of quickly look up, did something occur more than 4 times? And there's kind of one way people speed this up is using something that's called a Bloom filter. And so I want to quickly talk about this Bloom filter next. And it's kind of related to this. It's kind of related to the count per minute sketch. So it's going to be, I'm going to change topics a little bit. So any questions on the a priori algorithm? So let me bring the screen up. Okay, so what a Bloom filter is it's a really compact and fast data structure for keeping track of sets. So if you store a set, and you have objects which you can sort in some way, kind of the simple way to do it is you just keep them in like a sorted, balanced tree, and you can look something up in whether it's in the set in time that's logarithmic in the size of the set, right? So you basically need to do binary search to find it. And this works okay, but if you want to do this in constant time, it's going to be harder to do. And so a Bloom filter is something used in like routers and so forth, and is an extremely fast data structure. It has so you want to store a set, and you want to have so you want to do 2 possible things. You want to put some element x in the set. So it's going to store a set S, which is going to be, say, a subset of n. Let me use uppercase n. subset of n. You want to store this, so you want to put some object x in the set, and you want to check is x in S. So you want to check if an element is in the set. So these are the only two things you want to do. So this is going to have no no false negatives. So if something's in the set, it's always going to tell you that it's in the set. If it's not in the if it's not in the set, it may mistakenly tell you it is in the set. But with you can make it so it's a pretty small, very small probability. A small probability of error. So no false negatives. So you may say something is in the set even though it's not in it. Okay, and so that's similar to the Misha-Grise algorithm where we said it might be above a certain frequency, but there's a chance it was below that frequency, and we were wrong. So and this is again going to use so it's going to look like the min count sketch, but a much more compressed version. So what you're only going to store bits. You're going to store this array B, and this is going to go from B1, B2, up to Bm. So this is going to be m bits, and so you initialize that Bi equals 0 for all I. So now I'm going to have k hash functions where hi, so each of the hi's are going to go from the set n to m randomly. So these are these random hash functions again, where we're going to choose these from a set of hash functions, and we're going to choose k of them. Okay, and so now instead of, remember the count min sketch had a look kind of like this, where I had these, each hash function would go into these bits, and then I had k layers of bits. So I had k different hash functions, each with their own bits. Now I'm going to have all the hash functions go into the same bits. So all the hash functions are going to work on the same data set. Okay, so now the first thing I need to be able to do, so this is, so I want to put x in S. So what I'm going to do is for I, say, for j equals 1 to k, I'm going to set v of the hash of x equals to 1. Okay, so again, very simple. For each of the hash functions, I'm going to find its appropriate bit. So this is bi. And I'm going to set, so hash function j on x may point to here. And I'm going to set this bit to 1. And then I'm doing this for all hash functions. So they're all going to go into the same array. So I'm reusing the bits in some way. Right, so this is how I store something in there. I'm storing k bits, and k will be some number which is small. I'll tell you how to choose k a little bit. Okay, so if this is my data structure, that's all I do to put it in the set. How do I get something out of, how do I tell if something is in the set? How do I check, is x in S? So how do I do this?
Check if all of the edge ties that maps to the points have one.
Yeah, so I want to check all of the hash functions again. So I don't want to have, every time it's in the set, I definitely want to say, yes, it's in the set. And I know if it's in the set, then all of the hash functions are set to 1. Right? So I say if for all j equals 1 to k h of, or the bit h of x j equals to 1, then I return true. So this is if for all, then true. So I check all of the hash functions. If they're all equals to 1, then I'm happy. So now there can be some false negatives. Yeah, so I'm sorry. Yeah, this should be false positives. I don't know. Okay, so there could be something that's not in the set, and I say that it's in the set. I can have a collision. Right? So it could be that something is not in there, but all of the associated bits are also set to 1, right? So if I just have k equals to 1, right, then I'm just kind of, this is just kind of like a hash table, right? I'm storing something in there, and then I had a collision in the hash table. But the more I increase k, the lower the probability that this occurs. Right? Yeah.
Wait, so explain why it's false positives here?
Yeah, so I'm sorry, I totally screwed that up. So if x in S always true, if x is not in S, usually false. So if it's not in S and I say true, it is in S, then that's a false positive. I'm saying true being positive. It's true is like a positive that it's in there, and it's false. It's not the case. Right. So let's do a small example. Let's say my set. So my set is actually equal to 1, 7, and I have k equals to 2. So then hash of 1, let's say this is equal to 8. Hash of 2 of 1 is equal to 3. And then, so hash of 1 of 7 is equal to 4. And hash of 1 of hash of 2 of 7 is equal to 2, right? So then if my so if I have this if I have this bit array, it goes from 1, 2, 3, 4, 5, 6, 7, 8. So it starts out as all zeros, and I fill in a 1 here and a 1 here when I input 1 into the set. Sorry, let me switch colors again. Okay, so I put, if it's empty, it means it's empty. It means there's 0. When I put 1 into the set, I fill in a bit for spot 8 and for spot 3. When I put 7 into the set, I fill in a 1 for 4 and 2. And everything else is implicitly 0. So now if I want to check if 1 is in the set, I check bit 8 and bit 3, and they're both 1, so I say true. Right? So it should be clear that if it's in the set, it'll always return true. So let's say I want to check something 3, and so hash of 1 of 3 is equal to 4, and hash 1, hash 2 of 3 is equal to 6, well then 4 is a 1, but 6 is a 0. So that's okay. It was not in the set, and I returned false, which is the case. The set was 1 and 7, right? So now if I check, say I check the value 5, and this was 1 is equal to a 5 is equal to 8, and a hash of 2 of 5 is equal to 2, well then I see 8 has a bit that's 1, and 2 does 2, so this is going to return true, and so this is bad, so this is a, so this is a false positive. I return true, but the answer should have been false.
So I think you're right the first time. You can't have false positives. You can't have false negatives.
Yeah, you're right. So it has, okay. All right. Okay, good. So I think everyone is going to understand this better or be hopelessly confused. But no false negatives. And I'll put some false positives. If I wanted no false negatives and no false positives, I basically need to store I need to store something as big as the set. I need to actually store the set explicitly, in which case the lookup time would be slow, or I would need to store an array of size n, which may be too big. Okay, so let's try and look at the analysis of how well this works. So who's heard of a Bloom filter before this? So a few of you have heard of this. So who have seen the analysis before of, and you so the analysis most people show is a little bit, there's usually a small error in it, but it gives a good intuition of how well it works. And there's a very subtle subtle bug in the comment analysis, and to really analyze it, it's much harder. So we're not going to do that. So we're going to do the bad analysis, but it'll give you a good intuition of what's going on. Okay, so we're going to kind of go through here and kind of derive that the probability of a false positive, right? So so the probability is going to be roughly 1 minus e to the minus k m over n all to the power k. Okay, so this might not. So let me kind of explain what these numbers mean. So, and this is where n is going to be the number of distinct items in the set, right? So n is the size of S. M is going to be the number of bits And so k is going to be the number of hash functions. So usually, you kind of are given, you're usually given a budget of bits, and you can kind of estimate the number of elements you're going to put in. You may not know this exactly. And then but you can choose the number of hash functions. If you choose too many hash functions, you're going to have too many ones in there. And so then what's going to happen is you're going to have too likely of having a collision. If you have too small a number of hash functions, then you really only need one hash collision to happen in order to have one of these false positives. So you don't want too few, you don't want too many, and so typically you want so the advice here is to set k equals to roughly m over n times log base 2. So you roughly want to set k equals to this. So this is kind of a like a rule of thumb. So m over n. So if you're putting more items in the Bloom filter than you have available bits, you're not going to be able to. You aren't going to be able to do much. So this is how many m over n is how many bits you have per item you put in. Okay, now you might be thinking, well, what's happening if I have, if I have more bits than items, why don't I just store all of the items? Well, one really nice thing about this is I only need to store an array of bits. Right? I don't need to store like an actual label. Right? So if I'm storing like these, if I'm storing k-grams, I need to store an item may be characters, right? Or if it's a k-gram over words, it may be 2 words is each of the items. I don't want to actually store those words, right? If each item is like an IP address, this is going to take up 32 or 64 bits just to store one item. So instead, I can represent each item with roughly. So I'm going to set roughly m over n to be the this is how many bits I need per item times log of 2, which is slightly bigger than 1. So I want slightly more. This is slightly more than the number of bits I have per item. So this is often much smaller than storing the actual set, and it has very fast retrieval times. We'll see the analysis that it's very easy to implement, very easy to use, and we'll see that the probability of having of the false positives is very small. So. So we're going to kind of get to here, and actually the goal is going to be to get to this probability is actually we're actually going to get to 1 minus 1 over m to the km all to the power k. Okay, and so this is a better value of the probability. It's a bit harder to see what's going on here. So what's going on here is e to the minus something as this number this should be n over m here. And that is, this is an n. Okay, so this one's a bit easier to understand. So as this number gets large, this gets small, this gets close to 1. So you don't want this to get too large, because that'll cause this to be small, this will be close to 1. You want this to be much smaller than 1, and then you're going to take it to the power k, and it's going to decrease really quickly. Right? If you take something 0.5 to the power 10, it becomes very, very small. Right? If it's 0.9 to the power 10, it's also going to be very small. It's decreasing very quickly. So I want this to be as far from 1 as possible, so I want this quantity to be large. So I don't want this is kind of 1 over e to this power. So I don't want this to be too big. Right? So this is, m is the number of bits, this is the number of things in there. So this is already less than 1, so that's good. If I make k too much bigger than that, then this ratio, then this is going to become too large. And this will become close to 1, and taking it to the power k won't be as effective. So I want to set k, so this quantity is basically log 2. And so then this is going to be some constant. So then this is going to be, you know, some constant, and it's going to be far enough away from 1, and taking to the kth power is going to drive the probability down. So that's how to kind of look at this term. And I'm going to actually derive this property. Okay, so how do I get from here to this thing with the e in it? Right, so there's this trick that 1 minus 1 over, we'll say n to the power n. This is roughly, so the limit as n goes to infinity, you know, this is roughly going to be e to the minus 1. So then what this is saying is I can, did I get this right? So if I can take this m